The perturb and observe method, which was studied in the last video, was a fairly straightforward way to track the maximum power point of a solar panel. In this video, I'm going to talk to you about another MPPT technique that can be applied to the solar panel. It is called the incremental conductance technique. By now, you should know that the goal of maximum power point tracking is to find the voltage at which a solar panel or array of solar panels delivers the most power. These techniques can either be indirect or direct. The incremental conductance technique is a direct technique. This means that it directly scans the PV curve to find the MPP rather than using some assumptions and calculations to do it. However, incremental conductance is not as simple as the perturb and observe technique. Let's get into how it works. Here we have our normal solar panel IV and PV curves. When maximum power point tracking directly, there are three regions of interest. There is the maximum power point itself, and there is also a region to the left of the maximum power point, which is in blue here. If we are in this region, we need to increase the voltage to get to the maximum power point. Finally, there is the region to the right of the maximum power point, which is shown in pink. If we are in this region, we know that we have to reduce the voltage in order to reach the maximum power point. So, those are the three regions of interest. One thing that is unique about these three regions is the derivative of the power with respect to the voltage, or dP dV. At the maximum power point, dP dV is 0. In the blue region, to the left of the maximum power point, dP dV is positive. Finally, to the right of the maximum power point, dP dV is negative. So now you can see that if there is a way to determine dP dV, then we can easily determine which way to move in order to reach the maximum power point. The next logical question to ask is, how do we get dP dV from simple measurements? Is there a way to do this simply by looking at the voltage and the current output? Well, to answer this, we will look at the relationship between dP dV and the conductance. Conductance, which is designated by the letter G, is the ratio between current and voltage. It is the mathematical inverse of the resistance. Conductance can easily be determined by a simple current and voltage measurement. So how does this relate to dP dV? Well, since P is actually equal to the current times the voltage, or I times V, we can change dP dV to dI times V dV. Through the product rule, we can state that this is equal to I dV dV plus V dI dV. dV dV simplifies to 1, so we're left with dP dV equal to I plus V dI dV. Now, we can take that dI dV term and equate it to delta I delta V if the steps are small enough. This term of delta I delta V is known as the incremental conductance. So, we can rewrite the equation above as dP dV is equal to I plus V times the incremental conductance delta I delta V. The next thing we can do is to replace the incremental conductance in this equation with the negative instantaneous conductance, or negative I over V. When we do this, we can see that we get 0 as an answer. With this in mind, we can use the relationship between the incremental conductance and the instantaneous conductance to determine which side of the curve we are on. To explain how to do this, we can look at three different cases. Keep in mind that with all of these cases, we are comparing the incremental conductance to the negative instantaneous conductance. There are three cases, as I've said. The incremental conductance can be greater than, equal to, or less than the instantaneous conductance. Let's take a look at the first case. If the incremental conductance is greater than the instantaneous conductance, this means that dP dV is greater than 0. We solve this by comparing the two equations I showed to you in the previous slide. We get there by starting with the fact that dP dV is equal to I plus V times the incremental conductance. We know that the incremental conductance is greater than the negative instantaneous conductance. Therefore, we know that dP dV is greater than 0. This means that with just the incremental conductance and the instantaneous conductance, we are able to determine that we are on the left of the maximum power point, meaning that we should increase the voltage to get closer to the maximum power point. We can use the same formulation to realize that if the incremental conductance is equal to the negative instantaneous conductance, that means that dP/dV is equal to 0, meaning that we are at the maximum power point. Again, with just this comparison, we actually know we are at the maximum. Using the same logic, we can see that if the incremental conductance is lower than the instantaneous conductance, we can figure out that dP/dV is less than 0, meaning that we are at the right of the maximum power point. This whole concept is pretty counterintuitive, so feel free to take a moment to pause the video and look over this slide to make sure you understand the math that results in these relationships. So now you see our original plot. Using what we just calculated in the previous slide, we can change this to relate to the incremental conductance. So we know that if the incremental conductance is equal to the negative instantaneous conductance, we are at the maximum power point. If the incremental conductance is less than the instantaneous conductance, we are in the pink region, meaning a negative voltage step is necessary in order to get to the MPP. Finally, if the incremental conductance is greater than the instantaneous conductance, we are in the blue region. This means a positive voltage move will get us to the MPP. So now you can see that we can use this method to continuously track and find the MPP. The block diagram for the incremental conductance method can be seen here. As inputs, we need to have the instantaneous voltage and current, as well as the voltage and current from the previous measurement. From this, both the instantaneous and incremental conductances can be calculated. Based on this comparison, the next voltage will be calculated and then applied to our PV. The logic of the incremental conductance technique can be seen through this conceptual flowchart. I won't go through this in detail, but it will be available to you in the course platform. So that's the incremental conductance technique. It is a fairly counterintuitive technique for MPPT, but just remember that it is all about comparing the incremental conductance to the instantaneous conductance. The information indirectly tells us whether dP/dV is positive, negative, or 0, which in turn tells us which direction to move the voltage in order to get closer to the MPP. This was the last big technique you will learn in this course. There are other techniques that exist as well, and there will be some literature on some of these techniques for those of you who want to learn more.